Okay friends, now let us talk about the Ramachandran plot and what is the importance of Ramachandran plot in determining the conformation of proteins and the protein structure. Now what we know about the protein structure is the protein backbone is pretty much stable in nature because of the peptide bonds, because of the presence of the partial double bond character of peptide bond. But still, except for the peptide bonds, there are other bonds between C alpha C and also the bond between N C alpha of the peptide, and these bonds are actually have a freedom for rotation around the plane of 360 degrees. So you have the freedom of 360 degree rotation from plus 0 degree plus 1 degree to totally 360 degree angle is very possible in those cases. Now if we look at the diagram above, if we look at the diagram here, as we can see, there are torsional angles between planes. For example, the torsional angle between the C N C alpha and N C alpha C, which is called the phi, as well as the torsional angle between the N C alpha C and C alpha C N, which is psi. So these torsional angles are present there along this axis of the bonds. The peptide chain or the peptide backbone can be rotated at around 360 degree or up to 360 degree rotation is very possible. Now the question arises, as they are having the freedom for rotating 360 degree, all these rotations are all these rotations are fruitful in this case or not? The answer is no. Why? Because as we see in this picture below, if it rotates at a particular degree of angle, and a result of that, for instance in this case what we can see, after the rotation of the torsional angle phi of minus 60 degree and psi of 30 degree, it will represent its NH group as well as the CO group in very close proximity, which will lead to the generation of steric hindrance, which makes the structure really unfavorable. So though they are having a degree of 360 degree rotational freedom, but still all the rotation does not ensures a very good and stable polypeptide backbone structure. So what kind of rotational angles are actually helping them out to make a very strong, very stable structure? Now this question will be answered by looking at this Ramachandran plot. So what Ramachandran plot is providing us is the distribution of conformational angles in different proteins. Now the areas of this Ramachandran plot are there, which is actually helping us to understand what type of conformations and what type of rotations along this dihedral angles or torsional angles leads to the production of protein backbones, which are really stable in conformation, and also some of the protein molecules leads to the production via the process which is not being favorable. So both of the cases, Ramachandran plot helps us to distinguish between the distribution of the conformational angles which are favorable for a protein to be existed, and also some conformations which are totally unfavorable. Now in this picture in the left hand side, what we are talking about here in this Ramachandran plot, actually let me first describe what is how the Ramachandran plot looks like. As you can see here, so forget about these blotches and all these things, just think it is this 4 quadrant is there, and so one huge square, it is divided into 4 squares, and each of the squares represent the angular presentation. So if you start from 0 here and go towards the upper limit, that means plus 90 plus 180, and again in this direction also what we have minus 90 and minus 180. Now in the same orientation, if we start from here and look for this area, what we can find in this level, what we are having the phi, and in this y axis we are having the psi. So in x axis we are having starting from 0, 90, 180, minus 90, 180, and again in the for the psi on the y axis 90, 180 and minus 90, 180. Now as we know that we can rotate it throughout a plane, and this rotation will be 180 degree of rotation. So I have a mistake to tell that it is 360 degree, because 360 degree rotation in both the directions, but if you think about the rotation in a particular way, then it will have the freedom for 180 degree rotation. Okay, so that was a mistake, so don't go to that. But in this case what we are looking at in this Ramachandran plot is the division from 0 to 180 plus 180 and 0 to minus 180. Now what happens in this case, in this case, as we look in this upper limit and this 4 quadrant, the position of the amino acid backbone sequences having a particular torsional angle can be projected, and after the projection we can look for a standardized distribution for conformational angles, and by looking at the standardized distribution we can say whether this kind of conformations will be stable or not, or whether and what type of this torsional angles will be preferred to make the structure, the secondary structure of the protein molecule, whether this kind of torsional structure leads to the formation of favorable alpha helices or they lead to the formation of favorable beta sheets by looking at this hydropathy, by looking at this Ramachandran diagram. Now in this case what we are it is showing, it shows the statically allowed phi and psi angles for polyalanine. That means if we join alanine amino acids one by one together to make the chain, it will be called polyalanine, and it was calculated using the van der Waals distances between those CO group and NH group between those alanines. Okay, now if we look at here, then what we can find here in this picture, as we are looking at in this upper quadrant, as we can see, this part is really favorable for alpha helical bondings, and this part is also favorable, and again here we can see this part is favorable for beta sheet, as we can look. So this is this type of arrowing diagrammatic presentation tells us about the making of beta sheets, because beta sheets are most of the time parallel and anti-parallel in nature. So again in this picture showing the anti-parallel, this picture showing the parallel beta sheet. So the conformation which will have the positive 90 or a positive 90 to positive 180 degree angle of psi and minus 90 to minus 180 degree angle of phi, then it will provide some types of beta sheet. It will be the beta sheet production for those torsional angles are being favored rather than alpha helices and other things. Now if we look back to the second quadrant which is present here, that means the negative for, or the less than negative from 90 degree for psi and minus 90 to minus 80 for phi, then you can find this type of torsional angle. If we have a torsional angle production for a peptide chain like this, both of the minus, then it is a probable condition that they will form an alpha helices instead of beta sheets, or they have a tendency to form alpha helices rather than the beta sheets. But whatever we can have in this case, we can say that this Ramachandran plot will help us to know what type of protein structure those peptide bonds are going to be achieved. Not only that, but also are those protein structure being favored or not. But in this picture, as you can see, the distribution of different torsional angles, if we see the position of upper layer, and here is the lower, and this part of the layer which is also being placed to produce this alpha helices instead of beta sheets. But as we can see, these parts are favored, these parts are really favored part to make if we have a polypeptide backbone, for instance, and if we measure the torsional angles which will provide which leads to the dot providing this region or this region or this region of the Ramachandran plot, that will actually are helping us to know that those structural conformations are really favorable. But if we are having the we are after looking at those torsional angles, if we have a dot or if we have a point at the level of this zero or the zero diagram from here or here, this part of the Ramachandran plot are called the not allowed part, or this part of the Ramachandran plot is being not favored. So if we have a point at this middle range, that means we have a conformational array at this not allowed region, or the region at where we do not they do not allow the formation of any kind of bonds, any kind of peptide chain. Okay, so these things are really important. So by looking at these torsional angles and putting the values of these torsional angles into this Ramachandran plot or Ramachandran diagram, we can tell that what type of conformation they start to achieve, and they want to and try to achieve, and they favor to achieve. and by looking at the structures, and we can also say the what part is allowed and which part is not allowed. As we can see in this picture too, these parts are allowed and this middle part are the non-allowed zone. So whatever we can find this middle zone are not favorable conformation due to the presence of due to the spherical hindrance, as we have talked before. Now one very important consideration about this point, about this state, is whatever we are looking at, because of the rotation around the axis of this phi and psi angle, but still we have another bond, remember, that is called the peptide bond, which is really important bond to hold the amino acid structures together. But though they are not playing any role in the rotation, so they are restricting the rotation, if at all those peptide bonds have a chance for rotating. So if at all those peptide bonds will become any kind of single bond or single bond appearance, then those bonds will be rotated really quickly, and all this Ramachandran diagram will suddenly being changed, because if we are able to rotate along this peptide bond, that gives this peptide backbone enormous flexibility to rotate on itself, and due to the constriction around that single bond leads to the blockage of many different conformations of this peptide bond. That's a very important consideration, and just remember it for the whole time of your life. Okay, so that's all about Ramachandran plot, and I hope that's going to help you. Thank you.